In this video, we're going to talk about z-scores. But before we talk about z-scores, let's talk about measures of position. So measure position describes the relative position of a certain data value within the entire data set. So now let's talk about z-score. This represents the distance that a data value is from the mean in terms of the number of standard deviations. So the population z-score and the sample z-score is pretty much the same formula. It's the data value minus the mean divided by the standard deviation. So the z-score has no unit of measurement. It has a mean of 0 and a standard deviation of 1. So why do we use z-scores? This compares two different things by having the same mean of 0 and a standard deviation of 1. In other words, instead of trying to compare apples to oranges, we're trying to set it up so that we can compare apples to apples. So what does a z-score mean? If you have a z-score of 1 in 2500ths, this means that the data value is 1 in 2500ths standard deviations above the mean. If you have a z-score of negative 2 in 2/10ths, this means that the data value is 2 in 2/10ths standard deviations below the mean. Okay? And we will always round z-scores to 2 decimal places. Okay, let's take a look at a couple of examples. So the highest batting average ever recorded in Major League Baseball was by Ted Williams in 1941 when he hit .406. That year, the mean and standard deviation for the batting average is given. In 2014, Jose Altuve was the American League batting champion, batting average of a .341. In 2014, the mean and standard deviation for batting averages are given. Who had the better year relative to his peers, Williams or Altuve, and why? So we're trying to compare two different eras of baseball to one. This is where we're going to use a z-score. So let's start with Ted Williams. So again, the formula is going to be what? The data value minus the mean divided by the standard deviation. Okay, so plug in. His batting average was .406. The mean was this. And the standard deviation is this. So when you subtract and divide, rounding to 2 decimal places, we get approximately 3 8200ths. Now, let's do Jose Altuve. So again, data value minus the mean divided by the standard deviation. Well, his batting average was .341. The mean, which is given, divided by the standard deviation. So if you subtract first and then divide, you get approximately 2 5900ths. Right? Well, whose z-score is higher, Ted Williams or Jose Altuve? Well, clearly that is going to be Ted Williams. That is a higher z-score than Jose Altuve's. So Ted Williams had the better year. So let me write this out for you now. So Ted Williams had the better year since his z-score is greater than Jose Altuve's. Okay, let's take a look at the next example. So pizza parlor franchise specifies that the average mean amount of cheese on a large pizza should be 8 ounces with a standard deviation of 5/10ths of an ounce. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it's made of 6 9/10 ounces of cheese. Assume that the amount of cheese is below the mean by more than 3 standard deviations. The parlor will be in danger of closing its franchise. Is the pizza parlor in danger of closing its franchise? So here we'll use the z-score. So again, the z-score is equal to what? The data value minus the mean divided by the standard deviation. So in this case, the data value is 6 9/10. The mean that was specified is 8. Standard deviation is going to be 5/10ths of an ounce. Subtract and then divide, that's negative 2 2000ths. Again, remember, I'm going to round all z values to 2 decimal places. So, is this 3 standard deviations below the mean? In this case, it's not. So it doesn't look like the pizza parlor is in danger of losing its franchise. Let me write this out now. So no, since the z-score is not less than 3 standard deviations below the mean. Okay, one other example we're going to take a look at. So babies born after a gestation period of 32 to 35 weeks have a mean weight of 2,600 grams and a standard deviation of 660 grams. Babies born after a gestation period of 40 weeks have a mean weight of 3,500 grams and a standard deviation of 470. Suppose a 34-week gestation period baby weighs 2,400 grams and 40-week gestation period baby weighs 3,300 grams. Which baby weighs less relative to its gestation period? Why? So again, we're trying to compare apples to oranges right now. With a z-score, we want to be able to compare it apples to apples. All right, so let's start with 32 to 35 weeks first. Z-score, data value minus the mean divided by the standard deviation. So in this case, that's going to be what? 2,400. The mean is 2,600. Standard deviation is 660. So rounding to 2 decimal places, that's this. Now let's do after 40 weeks. So again, z-score is the data value minus the mean divided by the standard deviation. So this time it's 3,300 minus the mean divided by the standard deviation. To 2 decimal places, that ends up being this. So which baby weighs less? Well, remember, we're dealing with negative numbers, so which of those decimals is less than the other? Well, it's clearly negative 43 hundredths is less than negative 30 hundredths, so the 40-week gestation period baby weighs less. So let me write that out now. The 40-week gestation period baby weighs less than the 34-week gestation period baby, since the z-score of negative 43 hundredths is less than the z-score of negative 0.30.